So last time I'd started to introduce selection sort, and this is going to lead into quick sort, and in both cases we're going to do a randomized analysis. So the algorithms are not deterministic, or will not be deterministic once we make the modifications. And the analysis is going to be new, sort of a new style and different than what I'm sure most of you have seen before. So let me remind you what the select sort was, or selecting the kth smallest. And by the way, in the book, at least the version that I have, maybe there's a new printing, when they introduce this, it's in chapter 15, I think 15.3. But anyway, wherever they're talking about the select, they say that k should be the kth largest element. But in fact, it's clear from context and by looking at the algorithm itself that they mean the kth smallest. So in case that confuses you, remember that. Okay, so we had select sk, which means to find the kth smallest element in a set S. And the algorithm was to choose just some element S, AI, which I called the splitter. And then by direct comparison, by explicit comparing of AI to all the elements in S, we could collect S minus, this is the set of the subset of S of elements that are less than AI, and S plus, that's a subset which are bigger than AI. And remember, we made the assumption that all the elements in S are distinct, so there are no ties. And then we just look at the size of S minus. If S minus is equal to k minus 1, if that's the size of S minus, then we know that AI must be the kth smallest element, and so you can return it and you're done. But if S minus is greater than or equal to k, then we call select of S minus k, and we argued last time that when this occurs, we know that the kth smallest element in S must in fact be an S minus. And so we're still looking for the kth smallest in S minus. The final possibility is that the size of S minus is equal to a variable I'll call L, and that L is less than k minus 1. And in that case, we know that the kth smallest element in S must be in S plus. And so we're going to recursively call select inside S plus, and since we're now able to reject k minus 1 elements as being containing the smallest, the kth smallest, and also reject AI as being the kth smallest, then inside of S plus what we're looking for is the L minus k minus 1, the k minus 1 minus Lth smallest. Okay? So we recursively call select with S plus, looking for, with this parameter here, k minus 1 minus L. Okay, so that was the algorithm, and last time it is clear that it's correct, except of course we don't have a termination condition. So something up here, when the size of S is small, do something obvious to find the kth smallest. But otherwise, this is the recursive structure of the algorithm. And the other thing we did last time is we looked at what's the worst case running time of this algorithm. Well, one of the things that could happen is that AI might be the largest element in each one of these recursive calls. It's unlikely, but it certainly can happen. Well, actually, I shouldn't say it's that unlikely. If you have a deterministic algorithm which has a deterministic procedure for selecting AI, let's say the element at the end of the list or at the beginning of the list or something like that, some deterministic rule, you could certainly have data that's input where, for a systematic reason, the AI is always the largest one. You just don't happen to observe that, and you're unlucky enough that that happens. And when that happens, then at each recursive call, AI is the only element that gets removed. And so you're going to continually call select with this parameter only being, with S minus only being one smaller than it was the last call. Okay, and when you find S minus, the work that actually that's required to find S minus is, as I said, it's an explicit comparison of AI to every element in S. And so the amount of comparisons the first time is n, if that's the size of S, and the next time it's n minus 1, and the next time n minus 2, and so on. So you have a summation, essentially, from 1 up to n, and or if you're looking for the median, n over 2 up to n, whatever, all those things are of the order of n squared. Okay? So, this is, well, let me make it theta, n squared number of comparisons in worst case. Okay, but instead of doing this deterministically, we're going to change the choose to say randomly. Randomly choose AI. So it means with uniform probability. So for those of you who've studied a probability, had a probability course, you'll know specifically what I mean when I say uniform probability. For those of you who don't, I just just think of it sort of in the colloquial sense that every element in S has equal chance of being selected. Okay, so we're just going to look into S. S is probably held in some kind of array, and you're going to randomly select an index in that array where every index can be selected with the same probability as any other index. So that's uniform equal probability. And you choose an AI, and then you run this. And it's, of course, correct, because here, originally, we didn't say how you were going to choose AI. Any method of choosing AI would work. You're still recursively breaking into smaller set here, and you're making progress. So this is still a correct algorithm. But now the question is, what's its running time? Well, what do you even mean? What do we mean when we say the running time of an algorithm that has a random component in it? So this is not a deterministic algorithm. You can give it the same data one time, and it, of course, works. It finds the kth smallest, and it takes some number of comparisons. And then you run the same algorithm again with exactly the same input, and you run it again, and it could take a different number of comparisons. It'll still give you the same answer because we argue this is correct. But it could take a different number of comparisons, right? So the algorithm is not behaving, doesn't have to behave the same each time you run it. So in that case, we could just say, well, the worst case number of comparisons is still n squared, because even though this is random, you can still get that bad behavior. It's possible that you're picking the biggest element AI each time. But now it does seem less likely. Before we argued that you might get the biggest element each time for some systematic reason, that you're always picking the element at the end of the list or something. But now, since you're picking randomly, that is kind of defeated. That reason for why you might pick the biggest element each time is defeated. And you can get the intuitive sense that when you pick randomly, you're not going to have those kind of degenerate cases very often. And maybe that means that your typical running, I'm meaning this in a just purely colloquial sense, typical running of this algorithm would be better than n squared. That if you ran it randomizing, you really might expect, and I'm using that in a colloquial sense, you might expect that the running time is going to be better than n squared. Okay? Well, we want to formalize what this means. All right? So, first of all, just experimentally. Now, I know from last time not everybody has had a course in probability. This is why I'm kind of introducing this in a sort of colloquial terms first, and then we'll get into more precise probability terminology. And you have to use some results from elementary probability. But let's just say I do the following experiment. I run this algorithm on some particular data, particular S and a particular K. And I run it, and I count the number of comparisons that are done. 158. It happens to be. Right? 158 comparisons the first time I run it. Okay? Then I run it again with exactly the same data. And this time it's 152. And then I run it again with the same data, and it's 169. Okay? And then I run it again, and this is really, for some strange reason, turns out to be a lot more, 208. And then I run it again, and this time it's 120, and so on. Okay? What should I do with these numbers to give you some sense of how this algorithm is behaving in terms of the number of comparisons? What's a sensible way of trying to convey how the algorithm is behaving? I could average them. Okay, that's a very sensible thing. I could add them together, and then 1, 2, 3, 4, 5. It turns out this is 5. Okay, and that's the average number of compares in these 5 executions. And remember, it's executions with the same data each time. Okay? Well, the data has some size. Okay? Well, these numbers I'm making up have no relation to reality. And so if I tell you the size, what do you think for these kinds of numbers would be a sensible size for S that wouldn't be totally unrealistic? I mean, like if I said, okay, this is for N, this is for S having size 1,000. Does that make sense? No, that would be silly because these numbers are much less than 1,000. Okay, it's hard to imagine you can sort 1,000 numbers by only doing 158 comparisons. Okay, that means some numbers aren't even looked at. Okay, so I don't know what size list would these numbers possibly make sense for?
15.
50?
15 squared would be a little over 200.
Yeah, okay, 50 might make sense. Okay, so n equals 50 is possible. Maybe n equals 75. Later, once we do the actual analysis, we could go back and see what are sensible numbers. But in my thought experiment here, we have S of some size, and we're running it many times, and we're averaging the number of comparisons that are done, and if we did that, I could report empirically to you the behavior of this algorithm on this particular input and looking for this particular K. All right. Well, so I want to now talk about a random variable. I want to try to formalize this a little bit. A random variable call it Ni, is going to be defined as the number of comparisons done when running select, that's some particular input and some particular input. When running select sk repeatedly, it's the number of comparisons done when running select sk for the ith time. Okay? So again, it's the randomized version, and the first time you run it, n1 is the number of comparisons that are done. The next time you run it, it's n2, and so on. And so with this terminology, what we're talking about here was just n1 plus n2 plus n3 plus n4 plus n5, and then divided by 5. So we just have this, all I did was just introduce some notation. Ni is the number of comparisons that are done the ith time that I do the experiment of running the... but I have this other word here, random, or phrase, random variable. Ni is what's called a random variable, because it's a variable that takes on a value, that's what a variable is, where its value comes from something that has a random component in it. Some source of randomness is in there in assigning its value. And that's going to be my informal definition of a random variable. And since in this algorithm we have this random selection, and ultimately when you run it, some number of comparisons are done, Ni is a variable that gets a value, and that value is determined by some process that has a random component in it. So it's a random variable. Okay, so now what happens if we do this? Ni, I equals 1 through, I don't know, no, I don't want to use that. L, okay, divided by L. That's the average number of comparisons that are done if you do your experiment L times, right? So you do it L times. N1 was the number of comparisons the first time you did it. N2 is the number the second time, and so on. So if you add these all up and you do it L times and you divide by L, that's the average number of comparisons that are done. And that's something you can empirically compute for particular executions. Okay, any questions on what this is? And then in notation, does this make sense? Okay. And then what is this? Okay, now this is not something you can just compute empirically because L is now going to infinity. This is a concept, okay? And this concept is what's called the expected number of comparisons done when running select sk repeatedly, or infinite number of times. Okay, so this is a definition. This is what I'm going to use as my definition of the expected number of comparisons. Okay, and we'll leave it at that. But in this definition, S and K are fixed. So this is what you would get if you pick a particular S and a particular K, and you do this experiment. Okay. Now we're going to try to derive facts or learn something about this expected number of comparisons, and we're going to see that when we do that analysis, when we do that mathematics, it won't really matter what S is. I don't think it's going to matter what, well, yeah, in our analysis it's going to be valid for any K, although there are some Ks that are particularly simple, like k equals 1. We wouldn't have to use such a complicated algorithm. But we're analyzing this particular algorithm. And we're going to see in the analysis, the only thing that's really going to matter about these two parameters is how big S is. So we're going to learn something about the expected number of comparisons just as a function of the size of S. Number of compares only as a function of the size of S. Okay? So what we're going to learn is more valid or more interesting than if we were just going to learn something about a particular S and a particular K. But we started with a particular S and a particular K in order to introduce this notation of expected number of comparisons. All right? Now, this word expected, the first time I used expected, I said that's just in a colloquial sense. Now, this has a real mathematical meaning. It's this thing. And expected value, expected number, those are mathematically defined and have a mathematical meaning. Not necessarily equivalent to the colloquial meaning of expected. Okay? If I say I expect to find the bus at the bus stop at 3:10, then when I get there at 3:05 and I wait till 3:15, I'm kind of annoyed that it wasn't there because it's right there on the schedule, and I expect to find it there. That's the normal sense of expect. But and so it tells you if you don't see what you expect, that's some kind of anomalous occurrence. But an expected number of comparisons or expected value isn't necessarily what you really should expect to see if you do this experiment or compute this once over some real. And for those of you who have actually had a course in probability or statistics, what's the additional concept that would be brought in to kind of explain why the expected number is not necessarily the one that you most expect to see? Or actually, this is true, you most expect. But the expected number is not colloquially what you would be very disappointed not to see, if that makes sense. What's that added concept?
Mode. Mode.
Okay, mode, you're getting into the distribution of the values, but yeah. Is what? Yeah, variance. Okay, variance is an additional piece of information about the particular numbers that might occur. Okay, so and as we go further and further along in that direction, we get to the whole distribution of the possible numbers that can be observed. So you can have some values here, number, and this is the probability of observing it. And you can have a distribution that looks like this, so that no, I should have done it the other way. This is the number. These are the things that you're observing. And this is the probability. And what you're seeing, and this is just a few possible values in here. Well, anyway. In this sort of rough picture, what can occur is very tightly bound in here in a very small range. So the mean, or the expected value, is right there, and the variance is very small. And so in that case, you would be unhappy, you'd be surprised if you didn't see something pretty close to the expected, or the mean, expected number. But you could have a distribution that looks, like that, very, very broad. And it may, in fact, have exactly the same mean as before, but now because the distribution is so large, so broad, this has a much larger variance than the previous one. And when you have large variance, then you're not that surprised that when you observe a value from this distribution, it doesn't happen to be right there at the observed. Okay? So for those of you who've taken a course in probability, I hope just for practical sense that point has been hammered home. I happen to have read a book, well, it was about 10 years ago, called The Baltimore Case, which was about a Nobel Prize winner named David Baltimore, who's somebody in his lab actually falsified data in their lab experiment. And then he was on trial for a number of things. And the prosecutor confused these two concepts of expected value, expected number, and the mathematical concept, and the colloquial use of the word expected. So he was saying, okay, the expected number you should have observed from your experiment was 28, and when they did it, it was 32. It's not the expected, and therefore that proves that they must have falsified. And anyway, it was complete nonsense. But nobody among the defense and the jury and any of the people who were there at the time had enough knowledge of statistics and probability to really point that out. It was only later when they wrote this book about it they made such a big deal of the lack of common knowledge about expectation. Okay, so expected. So now, getting back to the question of what do we want to know about this random select algorithm, we want to know the expected number of comparisons that are done as a function of n. Okay, that's what we're going to derive. And worst case was n squared. Now, what's another way of finding, let's say you wanted to find, the kth largest. Or kth smallest. And you don't have to use this algorithm. Let's just say you can use any algorithm you like, but you want to get the fastest algorithm. What could you do? Yeah?
You could do merge sort and then just pick the minus one.
Okay, and what would that running time be? Yeah, you could sort. We know how to sort in n log n comparisons. You could certainly sort all of S. And if S is sorted, then you can just scan from one end and find the kth largest or kth smallest, and you're done. So we know that even though the worst case time for this algorithm is n squared, we know that order n log n is possible, and that's even a worst case. And if it's worst case, what's its expected number of comparisons going to be? If that's the worst case number of comparisons that are done, what's the expected number of comparisons that are done in merge sort? Or I'll put it the other way, what can you say about the expected number? It's what?
It has to be less than n log n?
Yeah, it's got to be less than or equal to that. This is saying, well, there's some constant here, which we didn't pay attention to, but there's some upper bound, absolute upper bound. Anytime you run merge sort with n, with a set of size n, the number of comparisons it does is at most c, so for some constant, times n log n. Okay? So if you were to actually run it repeatedly on the same data, of course, merge sort is a deterministic algorithm. So, at any rate, on that data, the number, as you averaged, you're averaging the same number each time. It's almost a silly concept. The number of comparisons is going to be less than or equal to that each time, and so your average is going to be less than or equal to that each time. Okay, so we know that n squared is possible, with this algorithm. N log n is possible with this algorithm. And what's the expected number of, what can we say so far about the expected number of comparisons using this algorithm randomly? Same kind of logic. If n squared is the worst case for this algorithm, certainly the expected number is going to be less than or equal to n squared. Okay, so what do you think it's going to be for this randomized select? And, yeah, n log n would be a good guess, and but in fact, we're going to get order n expected. That's what the expected number of comparisons is going to be. It's going to be order n. It's going to be linear in the size of the input set. Okay, and it's really, although this is a randomized algorithm, and so this is only an expectation. Sometimes when you run it, you're going to be bigger than n. Sometimes you're going to be smaller than n. And because this is a big O, there's a constant in here as well. And we'll actually be able to analyze what that constant is. It's pretty small. It's still worth, you should be impressed whenever there's a linear time, because when you take in data that has size n, you have to bring in each element one at a time. That costs you some time. If you're going to touch each element in the data, it, in the end, costs you at least order n just to touch it, just to get ready to process it, to do something with it. And if you can find the median or the kth smallest, which is something non-trivial to know, in time basically proportional to just the time to read it in, that's pretty impressive. So linear time is always impressive. Of course, this is an expected time. And, but I will mention that one of the great results, or early results in algorithmic computer science, is a deterministic algorithm to find the median that runs in order n time. But much more complex than this algorithm over here. So this algorithm, the select algorithm, finds the median in expected order n time. There's a completely deterministic algorithm that finds the median in order n worst case time. The analysis for the algorithm for select is much simpler than the deterministic algorithm is, and the analysis in both cases is, I would say, probably the analysis is harder in randomized. That's often what happens. Is the randomized algorithm is simpler than the deterministic algorithm, but the analysis is harder. Not all the time. Okay, so now I have to teach you two things about probability before we can start doing the actual analysis. So I've already taught you one thing about probability, which is this expected number, expected value. The second thing is, well, I want to put expected now we want to derive the expected value of a geometric random variable. Because this is going to be central in the analysis that we're going to do for select and then ultimately for randomized quicksort. So what's a geometric random variable? So a geometric random variable is equal to the number of times, the number of trials before success. Two C's, two S's, one C, one S, two C's, one S, one S, two C's. Who knows how to spell? Yeah. That's correct? Ooh, amazing. Before success, number of trials before success, when the probability of success at any trial is P. And P is less than or equal to 0. It's greater than or equal to 0, and it's less than or equal to 1. So as an example of this, suppose I take a coin and I flip it. Okay, if it comes up heads, that's success. If it comes up tails, that's failure. If the coin is a fair coin, what is P in that case? P is a half. I flip a fair coin, with probability of half it comes up heads, probability of half it comes up tails, and I can look at the number of trials that are done before success when the probability of success at any trial, any coin flip, is a half. But in general, it can be a parameter P. So I could be flipping a biased coin where the probability of a heads is 3/4 and the probability of a tail is 1/4. Okay, that's possible also. So then we would ask, what's the number of trials before success when the probability of a head was, what did I say, 3/4, and so on. Now, what's your general sense of which is likely to happen sooner? If the probability of heads is a half, or the probability of heads is 3/4, which one is likely to require fewer trials before success? But 3/4, yeah. It's more likely. Okay, so what I'm going to do again, similar to what we did over here, is think of, I'm taking out a coin, which is a probability P of success each time. I'm going to flip it until I get a success and count how many flips I did. That's the number of trials. And that's going to be the value of the random variable xi is equal to number of trials before success. I have to be careful. Do I want trials before success or trials until success? We'll have to be careful when we do the analysis. What's the difference between number of trials before success and number of trials until success? One trial. Right? It's just, am I looking at the number of trials just before there was a success, or the number of trials including that last trial when there was a success? So when I get, here I wrote before, but when we start actually doing the analysis, I may discover that I want it until. Okay. Xi is the number of trials before, or maybe until, I'm sorry for the ambiguity, before or until success. Okay? So xi is a, and what's the I here? On the ith experiment. Okay, the experiment is that I take the coin and I flip it until I get success. So I flip it and it's 3 times success. Okay, that's x1 was 3. I flip it again 2 times, x2 is 2. I flip it again 4 times, x3 is 4. Flip it again once, x1 is 1, and so on. That's if it was until. Number of trials, success. I'm being unclear here yet. All right, still. On the ith experiment, okay, then the expected value of x is equal to summation I equals 1 through infinity xi, sorry, not to infinity, over L, limit as L goes to infinity. So we're just saying, I'm going to keep doing these experiments over and over and over again and take the average number of flips that I do, number of trials that I'm doing, and take that limit as L goes to infinity, and this is the expected value of the geometric distribution. So everybody understand what this is, modulo this ambiguity of whether we're talking about before or until. And I think when we set this up, then we'll be able to answer the question of which it is. Okay, this is a mathematical definition of expected value of the geometric distribution. So let's see if we can figure out what that is. It's going to be a function of p, of course. That's the only real parameter in there. Okay. So p equals the probability of success on a trial, an individual trial. Q equals 1 minus p is the probability of failure on a trial. Okay? So now we can ask, what's the probability that xi is the ith experiment, okay, that we're going to do. What's the probability that that is equal to j? And of course, you can't answer that right now until you know whether the random variable we're interested in is the number of trials until success or before success. So I'll just tell you what I have written here, and then I'll let you tell me, was it before or until? Okay? Yeah. And this is actually, this won't answer that question, but okay, let me just show you what I have here. J minus 1. Oh, no, it does. It does. Sorry. Okay, well, I may have a little error in my notes, but what does this suggest now?
Before.
Is what?
Before.
Yeah, you're going to fail j minus 1 times. Each time is... actually, I don't have that in my notes. Page 1, page 2. Yeah, okay. That's what I should have. Okay, so let me ask the same question. This is now the probability of xi equals j. If it's that, now what's our interpretation of this? Is this the probability of j trials before failure or j trials until failure? J trials before success or j trials until success? Yeah. It's what? Until. Until, thank you. Yeah. So this is the probability of j trials until success. And why is that? Because you're saying j minus 1 times you're failing, each time with probability q, and 1 time you're succeeding, okay, with probability p. So the success is part of this term. And why, by the way, why are we multiplying? Each trial has a probability of p of success and q of failure. We're saying j minus 1 failures and 1 success, and the probability of that happening is p times q times q times q j minus 1 times. And I hope that everybody, just through some introduction to probability somewhere in high school, if not in a formal college class, understands that on independent trials, if the probability of success is Q, of failure is Q on one trial and Q on the next trial, the probability of 2 failures is Q times Q, and so on. So we're multiplying by Qj minus 1 times, and then finally you have success, and that's P. Okay, so now we can go back here and say all of this was until success. All right, so we now know what that is. So now, here this was xi. This was the ith time I did an experiment. What about the I plus first time I do the experiment? What's the probability that xi plus 1 is equal to j? That's exactly the same. There was nothing in here that depended on I. It only depends on j. So I'm going to just take that out of there because that's really irrelevant. Okay, so the probability that the number of trials I do until success is j is equal to that. All right, so now expected value of x. Now, the only way that we've had expected value before was in this sort of empirically oriented expression here. You summed up what you actually observed. You took the average, and you took the limit of that as the number of these experiments goes to infinity. But there's another analytical way of writing this, which is also true. It's summation j equals 1 to infinity of j times the probability that x equals j. And this is an elementary fact you would learn in a probability course. As soon as they teach you what expected value means, you would come to realize through some either formal derivation or just from working out some examples that if you take the number that's the possible number of trials until success, this is all the different possibilities. We're going to go up to infinity because there's no absolute bound on what that might be. You could get very, very unlucky and keep flipping this coin until infinity, and when you might finally observe, note that it's got heads on both sides, but or no, tails on both sides. It's been a failure each time. But each time, if you did the empirical thing, you'd be taking the average of what you actually observed. But analytically, it's going to come. It should converge to this, to j, which is the sum over all the possibilities. That's j, and each time multiplied by the probability that x equals j. And so you don't actually have to do the physical experiments repeatedly to find out what the expected value of this variable is, random variable is. You can work it out analytically. All right. Sometimes you can't solve this, but we will be able to solve it in this case. Okay. So in the geometric distribution, the expected value of x is summation j equals 1 through infinity of j times 1 minus, that's q to the j times p. Right? That's what we found out over here. The probability that x equals j is this, which I've written again over here, just inverting the p's and q's. You have to mind them. And then multiplied times j. Okay? All right. Now, how do we solve this? Anybody remember?
J to the
Yeah, first of all, we have to get it right. Thank you. P to the j minus 1. how do we solve this? Well, I can't. As far as I don't know if I could do this. Just seeing it for the first time ever. But there's a neat little trick, and I was going to show you it and do it all. I haven't got time, but it's posted on my website. There's a chapter on expected value, which has on page 38, I believe, in the class website, I tell you exactly where it is. It shows the complete derivation of what this sum is. And it uses a little trick of calculus, differentiation, and some other little sums. And you get to the following answer, you get to 1 over p. So you can read, if you want to see the real derivation of this with it's not that hard, it's a half a page long, but it's got a cute trick in it. If you want to see that derivation, you can look that up on the web, through the website. The book does it also, but they leave out the trick. They just show you it as if, the book has it on towards the end, they have a chapter on probability, but they just, what is the most essential point, they just sort of slough over. But anyway, this is the derivation, 1 over p. So what does this say when p equals a half? For p equals a half, the expected number of trials until success is 2. Okay? Let's take p equals 3/4. That's more likely to be success. The expected number of trials is 4/3, which is less than 2, right? So it sort of makes sense. Okay, this is the expected number. This is a fraction. So if you're not clear on how can you have a fractional number of trials, review what it means to be expected number or average. Okay. So this is the result, and if you want to do the full arithmetic and calculus that's necessary to do this derivation, look it up in class. Look it up in the class notes. I was going to do it here, but that would really just be showing off, It is a cool trick, I know.